let us continue a little bit the formal aspects of the story. I know it's a bit boring. Let me review the very basic things that we said. Not all the details, but the basic things. So one of the things that we said, for instance, is what is the meaning of the bra, okay? We said that in general a linear functional is something such that, so a linear functional is some application from the Hilbert space to the complex numbers, okay? Such that it is linear. So f of C1 plus C2 is equal to C1 f of C1 plus C2 f C2, right? Then we said we already know one. Psi phi indeed satisfies this thing, okay? So in some sense you can define phi psi given any vector, no? The linear functional defined in this way, okay? And then we said there is a theorem that somehow guarantees that any linear function can always be represented in this way. So an appropriate psi can be chosen such that you can always write it like this, which means that somehow writing this or writing this is essentially just a notational convenience, okay? Rather than define the functional depending on psi applied to phi, I write this object like that, which as you see has to somehow act on a state, okay? Is it clear? So in some sense bra are nothing but linear functional waiting for some vector to act on. Alright? Good. Now, this is one of the things we saw. Then we saw that for any Hermitian operator A, you can find a complete basis of states. So, for instance, let's start with a simple case. Some set of states phi n such that these are eigenvectors of the operator A, and these are the eigenvalues that, I remind you, are real. The set of all these phi n form a complete basis of the state. As written, the notation is a little bit insufficient because it assumes that somehow there is a state for every eigenvalue, while there could be more states associated to the same eigenvalue. In other words, a more general notation would be this: A phi n j equal to a n phi n j, where this degeneracy index, okay, j, runs from, say, 1 to some degeneracy number which I will call gn. Okay, so if gn is 1, then the eigenvalue en is an is non-degenerate. If it is 2, it's 2-fold degenerate. If it is 7, 7-fold degenerate, and so on. Okay? Good. We said that, for instance, let's keep working in this case. There is a particular meaning which you can associate it to an object like this. Okay? You see, this is a bit similar to this, in the sense that it must act on something, okay? Therefore, here you should always put somehow a vector. But contrary to this, the end result is a vector of the Hilbert space, which is this. So somehow this object here, unlike the functionals here, are operators, okay, acting on the Hilbert space and giving you a vector in the Hilbert space, okay?
and this is represented by, somehow by this structure. The bra to the right and the cat to the left. Okay? Is it clear? So, the meaning of this thing is a notation, remind you, meaning the following: Pn acting on psi, okay, is equal to phi n times the component of psi on the state phi n. Okay? That's the actual meaning. A number times this vector. The notation is somehow often adapted that you write it like this. Okay? Good. And we said that since this is a complete basis, okay, in fact, by summing over all n, this operator is phi n, so the phi n, well, let's write it like this. You essentially have the identity, okay? These are projection operator on the states phi n, but they form a basis, and we argued that if you project over all possible directions and you sum over all this, then you get everything, right? Obviously, this notation here is again a simplified notation. A better notation would be that Pn, more in general, is the sum from j equal to 1 to gn of phi and j, phi and j. So generally speaking, you have to project over all states within a given eigenvalue, okay, associated to that eigenvalue. Okay, if you do so, then you obtain the identity. And what else did we say? Well, one thing that is worth recalling is that if you use a basis that somehow is basis of eigenvector of A, then the matrix representing matrix form of A is particularly simple. We said that in general, given any basis, you have somehow the matrix of A represented by this object, okay? Elements of A acting on the element and taking the scalar product with that. But if you want the matrix element of A in between two eigenstates, okay? So suppose that we do first the simple case, non-degenerate, okay? Phi n prime, okay? What is this?
Matrix element of
this is an times phi n,
yeah,
right? Then you take the scalar product with that, and therefore this is equal to an, the delta of n prime n, okay? So if I have to represent this matrix, okay, it would be here A1, okay, here A2, in the diagonal, okay, and 0 everywhere else. Okay? What about the slightly more complicated case? So if I have here J and here J prime. Well, assuming that you have within each degeneracy space properly normalized and orthogonalized the basis states, it's the same thing. So this is the delta of n prime and the delta of j prime j. However, in general, A1 will be a block of a certain dimension, say here G1 times G1, okay? And here you will have 0 outside. And here as well, A2, 0, 0, and this is a block G2 times G2, and so forth, right? Okay? Is it clear? So, in the basis of its eigenstate, the matrix of A is diagonal and very, very simple. Fantastic. Okay. Now let us discuss what happens if I have an operator, an emission operator A and another emission operator B, and I want to search for a basis that is good for both. Okay? Generally speaking, if the operators do not commute, so if A and B commutator is different from 0, there is no hope. If you choose a good basis for A that is not good for B, not good means that the matrix for B in that good basis of A is full of numbers everywhere. It's an Hermitian matrix full of numbers in general. Okay? Vice versa, you could select a good basis for B and make it nicely diagonal, but then the matrix of A would be full of numbers everywhere. So, the only possibility is when this happens. Okay? If the two operators commute, then I can engineer a good basis which is common to both. Okay? This is something that I would like to show to you. Partially, mathematically, mathematical details are in the notes. The second part, however, I would make it lighter with the drawing. Okay? I prefer to convey the message with the drawing rather than do the part that is in the notes that is heavier and somehow you have to read it rather than listen. Okay, so let us set up the problem. Maybe I can fit it here. So suppose we have to somehow have labels now. Suppose that I have selected a basis of A, which I will call phi A and J. Okay, good. So this is the notation I have. Now, the first thing that I want to show is that if I apply the operator B to an element here, okay, phi and J, okay, then this object, remember, phi and J is an eigenstates of A with eigenvalue an. Okay? Let's see what happens when after I have applied B. So I try to see what is the action of A after applying B to this object. But the answer is simple. Since the two operators commute, I can write it as B, A, phi and J. Is it clear? Okay? I can actually interchange the two. But this is simple because this is an eigenstates with eigenvalue an, a number, a real number in fact. Okay? Therefore, being a number, I can just put it out because this is a linear operator, and therefore the result is an times B, phi and J. What does this equation, these two things, mean to you? I have taken, suppose that I was looking at the first block here, the first n equal 1, just to be definite. It means that here I have a basis which is phi 1a 1, suppose it was 3-dimensional, okay, just to be definite. Phi 1 2, phi 1 3, okay, for A. And in this basis I have A1, A1, A1. And everything else is 0. This is the matrix of A. Okay? Good. Now I take one of these vectors, any, and I apply B to it. And I notice that it's still in the same subspace. Okay? In other words, the eigenvalue, after, if you check and apply A, is still A1. Which means that it must be a linear combination of these three states. So, message, unfortunately, I need to write it in here, not correspondingly. The matrix of B, I'm pretty sure, will be here a block, say 3 by 3 or G1 by G1, with numbers, but 0 here, right? And 0 everywhere. Is it clear? Why? This proof here implies that the matrix of B must have 0 everywhere, except possibly in this small block, 3 by 3. Because applying B to one of these states leave you within the same subspace. The eigenvalue is not changed. Okay? So it must be a combination of those states. Is it clear? You can repeat the exercise, and any of the blocks that you see there do have this property. Okay? So the matrix of B in this second block will be something here and 0 everywhere else. Okay? And so for the third block and so forth. Okay? In other words, in the basis that I have originally selected for A, which is a good basis of A, B is block diagonal, is called. Okay? This is called a block diagonal structure, which is not yet what I want. I want a really diagonal metric, a common eigenstate of both. But it's already one step from the solution. Okay? Because all I need to do is to determine the right combination of, say, these 3 states which diagonalize this 3 by 3 block. And I can always do that, because this is, after all, a 3 by 3 matrix that I need to diagonalize. The elements here in the diagonal are always the same, so no matter what combination you take, the eigenvalue will be always A1. So you can change whatever mixture of the 3 vectors and will still be A1. And therefore, upon a suitable combination of those elements, I can in fact construct a basis where this becomes 0, and this becomes in general some B1, B7, B whatever. Okay, some eigenvalue. Obviously, if I order the eigenvalues of A, say in ascending order, in general, the eigenvalues of B will come whatever they are. Okay? No order. But I can guarantee that I can always diagonalize it. Okay? So in other words, upon suitably arranging and combining elements of the basis of A, I can construct a common basis of A and B. Okay? That's the message, mostly in visual terms, although in the notes you find more details of the algebra that in principle you would need. But that's not enough, that's not important. We will see very soon an application of this when we try to set up the angular momentum eigenstates. Okay? So in a very short while we will use this fact. Okay.
Can I ask you a question?
Yeah.
So what you just told us here is the basis of A can be both for A and B, but not necessarily. But I can multiply B by the basis of A and I get new basis. But then I can diagonalize and I have basis for both.
I don't know if I understood correctly what you say, but what I meant is the following. Let's do it simpler, two-dimensional. Suppose that this object was a 2 by 2 block. Okay? So I have two elements, phi A1, 1 and phi A1, 2. Okay? The block of A, okay, in this basis is obviously A1, 0, 0. Okay? The block of B is unfortunately, in general, a number. Okay? Let me call it X. let me call it, no, x, y, and z, z star. Okay, these are real, and these are complex and emission conjugate. Okay, because it must be an emission metric. Good. Now, the point that I wanted to say is I can always make combination of these two states. Okay? For instance, let me just define alpha times phi A11 plus beta phi A12. Okay? That's a combination of these two states. If I ask you, let me call it psi. If I ask you, what is the eigenvalue of this combination for A? The answer is, well, A1. Okay? This would be as good as these two states as being one state of the basis. Is it clear? In other words, I can form the first element, phi1, with an element A1, alpha 1, and beta 1. Okay? And the second element, psi 2, with an element gamma 1 and delta 1. Okay? Whatever alpha, beta, gamma, and delta I choose, these two states are as good as these two. Okay? So I could use them in place of these two. And the matrix of A would be the same. That's the first message. Second message, by using this flexibility on the parameters, okay, I can now look for parameters such that the matrix of B is diagonal. Can I do that? Well, all I have to do is diagonalize a 2 by 2 matrix, which I can always do that, right? It's very simple, in fact. In general, the matrix might be larger and the process might be more complicated. You have a computer to do that. But the conceptual difficulty is just finding combinations which diagonalize the block which is non-diagonal, which is something that you can always do. Is it clear? Okay. Good. So let us finish this rather dry abstract kind of presentation with a few more comments about wave functions in real space, in momentum space, because that's useful.
I can do this, right, for more than 2 operators?
Of course you can go on.
Okay.
Yes, absolutely. I did it for 2, and I find the basis good for 2. But if I have a third operator that commutes with both of them, in general the third operator will be block diagonal and dot diagonal after I have done all my first job. Okay? And I continue, and I find new combinations that somehow, okay? So until I can, if I have a set of commuting observable, I can find a basis that is good for all of them. Clear? Okay. In practice, we will see some of this. For instance, in doing the hydrogen atoms, we will see that we can construct the Hamiltonian, the total angular momentum L squared, and Lz, more about these two objects in a while, and all of them commute among each other. Okay? So I'm guaranteed that I can find Hamiltonian eigenstates which are also angular momentum eigenstate with a given definite component of angular momentum Lz, because of this theorem. Okay? But we will do it in practice, so you will see illustration later. Okay. So we said, given a basis of an emission operator, there you have the projection operator, and with this object, in principle, if you sum overall possible values of the eigenvalues, okay, you have a so-called resolution of the identity. very useful very often, okay? You have some equality and you can say, let me put an identity here and use as a basis over which I construct the projection operator eigenstates of something which I like, okay? You can insert these things and do lots of interesting algebra often with this trick. But what I want to tell you now is the following. We discussed that the position eigenstates are a bit tricky. They are somehow infinitely localized state in space, and the momentum eigenstates are also a bit tricky. You might say, where did we see the momentum eigenstates? Remember, we said that these are momentum eigenstates, the plane waves. You might say, but wait, this is a ket and this is a wave function. Okay? So generally speaking, when I talk of a wave function psi of x, what I mean is the scalar product of the position eigenstates with the ket psi. Okay? So what this is nothing but the scalar product with the position eigenstates with the plane waves, with the momentum eigenstates. Okay? That's the meaning of this object. Both are rather strange. They are either very singular or not normalizable over the infinite volume. Nevertheless, they are very useful, especially in intermediate manipulations. Okay? For instance, let me just show what you can do with these things. The first thing that you can do is, by just generalizing this, you can say, okay, the identity, I can always write it as an integral over all points in space of the position eigenstate projector, okay? Xx, pretty much as here you would write something like sum over n and j, whatever, okay? Phi and j, okay? Is it clear? Now I write that. Okay, good. Therefore, if I have a state, okay, I can rewrite it as identity times the state, but the identity is the integral over dx of x times the state, but x times the state, we said, is the wave function, okay? So here it is an expression for a generic state as an integral with the wave function of position eigenstates, okay? That's already something which you can always write. Fantastic. Then we said, okay, we have the plane waves. Let's call them phi k of x. Okay? These are the plane waves. Good. Let's in fact use a slightly different normalization. You'll see in a second why this is useful. In 3 dimension, let's put the square root of 2 pi cube there. Okay. Now, to appreciate some of the peculiarities of these states, let's try to calculate x scalar product with x prime, 2 different points. Okay. Here is the first case where I use something which is insertion of an identity. But this time, rather than using this, let me just insert identities with position eigenstates. Okay? I can use one of the two. In fact, let me use this. So I write x, the identity, x prime, okay? Which means integral over dk, this time, of xk, k, x prime. Is it clear? Okay, good. I know what this is. This is written here. Okay? So this is equal to integral e over dk of 1 over square root of 2 pi cube e to the I k dot x. Well, what is this? It's the complex conjugate of the same object with x prime. So let me write it like this. And let me just eliminate this because I have two of them. There it is. I have calculated, let me in fact write it here, that the overlap between two position eigenstates is in fact this rather funny looking integral of plane waves. Now I sent you a while ago appendix B of the notes, which is an appendix on the Dirac delta function. Please look at them. And you will see that you can make sense of this thing as being the delta function of x minus x prime. Okay? Please look at the couple of pages where you see different ways of representing Dirac delta function. Quite useful in practice, by the way. Okay. Second thing, suppose that I ask you, okay, no, I don't want this. Let me just calculate the scalar product of two position eigenstates, k and k prime. Then I do almost the same thing, except that now I insert an identity with this. Okay? So this is an integral over dx of k x x k prime. Is it clear? So what is this? This is the star of this object here. Okay? So here, integral over dx of e to the minus I k dot x divided by square root of 2 pi cube. And what is this? It is almost the same thing, except that here I have, let me write it as e to the plus I k prime dot x. Okay? And again, there is a factor here. So the object is integral over dx over 2 pi cube of e to the I x, this time, k minus k prime. Okay? Now, apart from having a different names in the variables, these are exactly the same integral. So the object that you have here is once again a Dirac delta in momentum space.
So
Good. Yeah.
using these equations like the scalar product of position, bras and kets, can we say that the bra vector of, for example, x vector has a dimension? Because the Dirac delta is dimensional.
Sure.
So,
In some sense, yes. Well, I mean, you can also see from here. You see, this object has to have no dimension, but here you have length. So, yes, certainly.
yeah.
Position, I guess, they have a dimension. Yes. Which is, I mean, a counterpart of that. The dimension of this comes from the fact that if you integrate over x, some function, any function, okay, with this delta of x minus x prime, you obtain f of x prime, right? So the dimensions here and here are the same, which means that the dimensions of length that you have here has to be perfectly cancelled by the dimension of the delta, which if you read is almost the same thing as written there. Okay? Good. So far it's clear, right? So these are the two overlap. You see, rather singular objects with singular kind of, before we were discussing things where the scalar product of two elements of the basis were Kronecker delta. These are funny and singular states, eigenstates of momentum and position, and their scalar product is a bit more singular, which is the Dirac delta rather than the Kronecker delta. Okay? Final thing, let us make reference, let's switch from one to the other and see how direct and inverse Fourier transform are essentially there on the blackboard. Okay? So let's try to do this. Good. So the starting point is, for instance, this. Before I wrote that psi is equal to the integral over x of psi x times position eigenstates, where this object here was x psi. In a precisely similar way, by using the identity as here, I can write this as the state as an integral over k of, let me call it, well, never mind, k psi times k. Okay? Simply using this object. So, this object has somehow the natural, it looks like a wave function in momentum space. Let's be a bit more explicit. K, let's see what k psi is. Well, let me insert an identity of x. So this is equal to the integral over x of k x psi. So what is this? Integral over x of the start of this. So e to the minus I k x over square root of 2 pi cube times the wave function of psi of x. Okay? Now, this object here, without the 2 pi factor, physicists would call it psi of k, the Fourier transform. Okay? Notice the hat here is not operator, it's the Fourier transform component. Mathematicians are in fact very symmetric, and they define the Fourier transform including the factor 2 pi cube square root. Okay? While we physicists like phi of k without square roots, and we just put all the 2 pi cube in the inverse Fourier transform. Okay? Good. So this object here is, apart from possible 2 pi cube square roots, the Fourier transform of the state. Okay? So you can write a state as an integral over wave vectors of the Fourier transform of the wave function times position eigenstate. Fantastic. And then let's look at the final expression, which is this. Let's consider now psi of x. By definition, that's x psi. We have said. Okay, let's insert an identity in the form of this. So this is integral over k, x k, k psi. Okay. Now this is equal to integral over k. This is e to the I k x divided by square root of 2 pi cube. And what is this? Well, we wrote it there. Is the Fourier transform of the wave function divided by square root of 2 pi cube. Okay? So the result of this calculation is the integral over k over 2 pi cube of e to the I k x times psi. What is this? The inverse Fourier transform. Okay? So you can go back from position state or momentum eigenstates. They are both singular, both have a Dirac delta. You can go back and forth essentially by doing Fourier transforms. Okay? And generously applying these objects, although they are somehow stranger objects than just normalizable states with their Kronecker depth. Okay? So please be relaxed. Just do it. It comes out right. Okay. Good. This ends this dry part. Okay, now we dive back again into a little bit of more physical thing, and we have to make a new acquaintance, okay, which is angular momentum. So the remaining trajectory of our study is we encounter angular momentum. We do a general construction of seeing what are the eigenfunctions of angular momentum in general. Then we also discuss about spin, because it's a peculiar and simple case of angular momentum, which is, however, not associated to spatial wave function, but rather to an internal degree of freedom that was discovered somehow experimentally and then formalized by Dirac. And then with all this machinery we discuss a little bit of the measurement in quantum mechanics, which returns back to this abstract story we have done. Finally we do the hydrogen atom and then a few other things. Okay? So that's the trajectory of our next few lectures. So let's start with the first new operator that you can think of. Remember, so far I had x, the position eigenstate, the position operator. Let's I should put the hat. Okay, let's put the hat. And p, the momentum eigenstate. I know that they do not commute, and they have, in fact, they have a commutation relationship like x alpha p, say beta, is equal to I h bar delta alpha beta, where alpha and beta are Cartesian coordinates, can be x, y, or z. Okay? Is it clear? Good. Obviously, I mean, just notation. When you think of xx, okay, the x component of the x operator vector, just let's denote it by x, okay? X component y, let's denote it by y, okay? So sometimes I will just simplify a little bit the notation. But that's in principle the general expressions that you can write. Now, in classical physics, you know that you have the following object. Vector product of the momentum and position. And this is the angular momentum of a particle revolving around some origin, for instance. Okay? In precisely the same way, you can define the orbital angular momentum in quantum mechanics. Okay? So you take the position, you take the momentum, and you take this vector product. And you form what is called the orbital angular momentum. This is for a single particle. If you have more particles, you have to sum over all particles. Things become a little bit more complex to handle, but conceptually is a simple object. Now, however, careful, because these operators in general do not commute when they have the same index, remember. So, for instance, suppose that I ask you to write Lx. Okay? Now, remember how you calculate the vector product of two vectors? You take the component y of this times the component z of that, okay? Minus z component y, okay? Now you might say, but, okay, but these two commute. That's true. For the time being, the issue of commutation is not crucial, okay? So that is just a standard expression that you might write for the x component of an angular momentum vector in classical mechanics, okay? All right, let's do it for y. And here you have zpx. I will omit, okay, from now on, if you allow me, I'll omit the hats, otherwise I get crazy with okay, sorry, minus pz. And Lz equal to xpy minus ypx. Okay, these are the three angular momentum operators. All right. Now you can say, do these three operators commute? The answer is absolutely not. Okay? Let's see, for instance. Let's suppose that you want to calculate Lx and Ly. Okay? Then, well, in principle, we have the expression, so it is, for instance, y pz minus z py commutator with z px minus x pz. Okay? Let's try to do it together. I'll go slowly. There are four terms, 2 times 2, so 4 commutators. Okay? So let's see. One is y pz commutator with z px. Another is minus y pz commutator with x pz. Another is minus z py commutator with z px. And finally, I have another term which is the plus plus, which is z py commutator with x pz. Okay, these are the four terms. Let's start looking at these two guys here. You see, x pz commute, x and y commute, pz and pz actually commute. So if you do all your algebra of commutator of products, that you know how to do it. By the way, remember, I know that if I have an operator A times an operator B and I want to do a commutator, that's equal to, you take A out, B commutator C, plus A commutator C, you take B out, okay, in this direction. Okay? So you can do it, but needless to say, this is 0, because everything commutes with everything else here. And here as well, z and z, and this is py, and this is px, okay? Different components of momentum, by the way, commute as well, right? Because the derivative in different direction. Is it clear? Okay, so these two actually disappear. The only thing I need to take care of are these two terms. Okay? And here, the two nasty guys are these two. You see? Because these two objects do not commute among each other. You have to do a couple of applications of that thing, but you would understand that the net result of this thing is the following commutator here. Okay? So the two things give you a non-vanishing commutator, and y can come out and x can come out. Okay, so this object here is equal to minus I h bar y px. Okay. Good. What about this object? This object, you can write it in a rather similar way. Just take minus the commutator of x pz with z py. Okay, just exchanging the two things. And then it's precisely the same object, except that there is a minus and there is an interchange of x and z. No, well, what is it? Sorry. I think I'm, did I write it correctly?
Yeah, it's correct. It's plus IH.
Yes, it's correct. So this is equal to minus and minus, so it's equal to plus IH xpy. Okay? Good. So it always takes a little bit of care and everything. So the result of this commutator in the end is IH bar, we'll put it in front, xpy minus ypx. Okay? And then you stare at this object and you discover this is HC. Okay? So the result is IH bar LZ. And this is true in cyclic order for the others. For instance, you can prove that Ly commutator with Lz is equal to IH bar Lx, and Lz commutator with Lx is equal to IH bar Ly. Okay? I don't want to do it, it's very boring, but after a while you understand that there is a trick of cyclicity, and therefore you almost you believe it. Okay? In fact, these three commutations can be written in the following way: L alpha, L beta equal to IH bar epsilon alpha beta gamma L gamma. Well, let me explain to you what is this epsilon. It's the same antisymmetric tensor that presumably you have found in doing vector products. If you remember that I can, if I have a vector A and I take the vector product with the vector B and I want the component, Cartesian component with gamma of it, then the result is epsilon alpha beta gamma A alpha B beta. Okay? This means, by the way, a convention, sum over repeated indices. Okay? And here as well. But the interesting fact about this object that is essentially mostly zero, except for 1 and minus 1. For instance, epsilon x, y, and z is equal to plus 1. Okay? If you exchange any of the two index ones, you get a minus 1. But if you exchange two of them, you get a plus 1 again. So for instance, just to epsilon y x z would be minus 1. But epsilon y z x, okay, would be plus 1 again. If two indices are the same, for instance here, x, x, z, then since when you exchange things you have to change the sign, you deduce that it must be 0. Okay? So in order to have an anti-symmetric object, indices cannot be the same. If they are the same, the element is 0. Okay? With these very simple rules, you know that this object has exactly the right zeros and plus and minus to express a vector product. Okay? And in fact here, for instance, if I have x, y, let me just exemplify this. Okay? Then according to this thing is I, h bar, epsilon, x, y, then I have to sum over gamma, but what is the only possible value that this index can have in order not to repeat any of this? Z. Okay? So it's enough to have this. And what's the value of this? Plus 1. Okay? And in the same way, you deduce that all the others are nicely reproduced. Is it clear? Good. So these are the commutation relationship of orbital angular momentum to be contrasted with the canonical commutation of x and p. You see, there is no delta. There is a momentum, angular momentum also to the right, and there is this funny antisymmetric matrix, tensor there. Okay? Good. That's enough for the intro. Now let's further enter into this business. And the first thing that I want to show to you is that the angular momentum operators you see they involve in general all coordinates or momenta, right? But I want to convince you that if I write in a spherical coordinate x as the distance from the origin, do you remember the spherical coordinate, right? I write them times sine theta times cosine phi, the y as r times sine theta sine phi, and the z as r cos theta. Okay, these are the Cartesian, the spherical coordinates. Remember, okay, let's draw it. This is x, this is y, this is z. I have a point here. Okay, I call theta the angle of the parallel on the Earth. Okay, from the North Pole. And then obviously the component along z is simply the distance from the origin times the cosine of theta. The piece on the plane is r sine theta, this two. But then if I want the component along x, I have to add phi, which is the longitude counted from x. X is Greenwich. Okay, say. All right, good. So phi can go from 0 to 2 pi, theta from 0 to pi. Right? 0 North Pole, pi South Pole. Good. These are the Cartesian components. Now I want to prove for you that these three operators, although in principle they involve distances from the origin and derivatives and so on and so forth, they only depend on theta, phi, and derivative with respect to theta and phi. This is a nice, interesting thing. After all, it's angular momentum. It's related to rotations, and therefore the distance from the origin has to somehow disappear. It does disappear. Okay? Let's do this algebra. Not the most entertaining algebra, I must tell you. So let's look at the clock. Let's hope that it goes fast. Okay. If I have a derivative with respect to r of some function, okay, which depends on the position, what can you do? You say, okay, let me just take a derivative with respect to x of the function and take a derivative of x with respect to r, plus a derivative with respect to y, and then a derivative of y with respect to x, r, plus a derivative with respect to z times the derivative of z with respect to r. Is it clear? Now you see here the component, the Cartesian component of the gradient, derivative with respect to x, y, and z. What are those objects here? This thing here, this thing here, this thing here. They are components of a matrix called the Jacobian, of the change of... But nothing could be simpler, in fact. What is the derivative of x with respect to r? Y with respect to r? Okay? Good. So the first, our first line is essentially the following. The derivative with respect to r of anything can be written as the sine theta cosine phi, sine theta sine phi, and cosine theta, because these are the three derivatives that you have there, times derivative with respect to x, derivative with respect to y, and derivative with respect to z. Okay? Anything that you put here, because you see there, I have eliminated any notion of f. It's a function that I have to apply this operator. Is this way of rewriting that expression clear? Okay? I suppose that this was an f. Okay? Derivative of f with respect to r is sine theta cos theta, because that's sine theta cos phi, times the derivative of f with respect to x, plus this, plus that. Okay? Clear? Good. First step. Let's do the second. Suppose that I have the derivative with respect to theta of a function. Then you might say, well, I do the same. It's the derivative with respect to x of the function times the derivative of x with respect to theta now, plus y d theta plus z d theta. Is it clear? Okay. Now, before the derivative was trivial, just eliminate r. Now it's slightly more complicated, but only slightly. The derivative of x with respect to theta. There is a sign. Is cosine, right? So here I have r times the cosine of theta times the cosine of phi. What about here? The derivative of the sine is still the cosine. R cos theta, say cos phi, sine phi, sorry. And what about the last? Minus. Good. Minus r sine theta. Okay? Is it clear? Good. All of them have a factor r. Okay? So let me just calculate 1 over r. Okay? And if I do it 1 over r, this factor goes. Okay? Good. Now I put this in my 1 over r, the derivative with respect to theta of any function f. Sorry, let me write it like this. Of any function f equal to, second line, here I should put cos theta, cos phi, cos theta sine phi minus sine theta. Okay? And although I know it's very boring, let's do the third thing. So the derivative with respect to phi of f. That's equal to the derivative of f with respect to x times the derivative of x with respect to phi plus, I erased this because we used it already, derivative with respect to y, y with respect to phi plus z, z with respect to phi. Now, in fact, z doesn't depend on phi, so here I have a nice 0. And what about the derivative of x? Cosine is a minus sign. Okay, so this is minus r sine theta sine phi. And what about this? This is r sine theta cos phi. Now you see that the common factor is this. Both of them have this.
Yeah.
Okay, so why? Let's do 1 over r sine theta, the derivative with respect to phi, okay, of any function, according to what I've written there, is minus sine phi, cos phi, and 0. Do we agree on this? Okay? What we have painfully done is to derive a relationship between the gradient in Cartesian coordinate and the gradient in spherical coordinate. This is written in almost absolutely in every book in electromagnetism. Somewhere on the cover or hidden, there is a relationship like this. Okay? How to transform the gradient from Cartesian to spherical coordinate. That's what we have done. This is not quantum mechanics, it's just calculus, vector calculus. Okay. Good. In fact, so I eliminate now the function f because that's somehow true for any function that you might want to calculate. Okay? Now let me write this in the following way. Rather than writing the matrix like this, let me write it in a transpose way. So I write sine theta cos phi, then sine theta sine phi, and then cos theta. You see the first row is now first column. The second is second column, cos theta cos phi, cos theta sine phi, and minus sine theta. And the third is minus sine phi cos phi 0. Okay? Transpose, obviously. I just transposed it, and therefore I have to indicate that this, the transpose of this. You might ask, are you crazy? Why do you want to actually do that? I mean, just follow me for a second. Okay, let us look at the first column of this matrix. This is a matrix, okay? Let me call it O. It's an O, but O. The first column of it is sine theta cos phi, sine theta sine phi, and cos theta. What is this? Do you see anything like this on the blackboard?
X over X minus
Okay? So this object here is in fact the vector x divided by the distance from the origin, which one usually calls the versor, the unit vector, okay, in the radial direction. Okay? Is it clear? Okay, so that's the unit vector in the radial direction. Very nice. What about this object here? By the way, you can check that the square of this plus square of this plus square of this plus your simple trigonometry is 1. What about the square of this plus square of this plus square of this? You see, this is cos squared times 1 plus sine squared. So it's again a unit vector. Hint. It's a unit vector in the direction in which theta increases. Okay? You can verify. It is, by the way, orthogonal to this. Take the scalar this times that plus this times that plus this times that. Do the other and you will see magically 0. Okay? So it's in fact a versor in the direction of increasing theta. So somehow, if I have here the sphere, okay, the direction of increasing theta is the meridian, right? Good. And what is, so this is theta. And what is this? Guess is the third unit vector, the phi, in the direction of increasing phi, which is along a parallel, okay, on the Earth. Phi. Again, something whose square plus square plus square is 1, orthogonal to the 3 previous ones. So these are the 3 moving because each point is a different set of these 3 vectors. Vectors that somehow define the unit vectors of the Cartesian spherical coordinate. Radial, tangential, and longitudinal. Okay? Is it clear? Very good. Now, let me just... I want exactly the opposite transformation now. I want this vector, Cartesian vector, in terms of this derivatives with spherical coordinates. So I have to invert this matrix. Okay? And now you might feel a bit depressed and say, hey, if it took 10 minutes to write it, then now he has to invert it. It would be a mess. Right? But there is a nice property of this matrix. The matrix is orthogonal. In fact, you see, it's made of 3 orthogonal vectors. So by definition, it is an orthogonal real matrix. And you know that orthogonal real matrices verify the following thing. The transpose times O is equal to O transpose is equal to the identity. Okay? Therefore, the inverse of a given matrix is in fact equal to the transpose. Okay? So if I have to write for you the this on the left and this on the right, all I need to do is to eliminate the t there. Okay? So in other words, okay, let me write it here. dx, d in dy, d in dz equal to the very same matrix that you see there. I don't write it. So the matrix where here I have R, here I have theta, and here I have phi times d in dr, 1 over r d in d theta, 1 over r sine theta d in d phi. Is it clear to everybody? Okay, good. That's already something very, very useful. Why? Remember, this object here is what I would denote by gradient. Okay, it's the three Cartesian component of the gradient. What this way of writing is telling me is the following. Let's write it here. Maybe I can also erase some of the intermediate steps. Bear with me, we are towards the end of the tragedy, okay? So the gradient equal to R times, I write it first, and then you tell me if you understand it, plus theta 1 over R d in d theta plus phi 1 over r sine theta d in d phi. Do you understand it? Okay? So the x component is the x component of this times that. Okay? Plus the x component of this times that plus the x component of this times that. Right? The y component is the y component of this times this plus the y component, so on and so forth. Okay? So component by component, that's exactly what you have there written as matrix and product. Okay? Good. Now, this is what I wanted to have. Okay? So 10 minutes of sweat, of derivatives, but rather elementary, as you saw. To have the expression for the gradient in Cartesian coordinate expressed in terms of the three unit vectors of the spherical system and radial derivative, theta derivative, phi derivative. Okay? That's the transformation that I told you. It's in every book in electrodynamics. Good. But now you remember that P is equal to minus h bar the gradient. Okay? X is equal to R times R. Right? The vector is the length times the radial direction. Okay? And now I want to do L, which is X vector product with P. So what I have to do is R times the radial vector, vector product with the gradient, and there is a minus I h bar that I have to keep track of. Okay? Is this clear? Now, R vector product with something which has three components, R, theta, and phi. Let's see. R with itself, what do you think we'll do?
0.
0, very nice. R with theta. This times that. 5. The screw law. Or the right hand side law. Okay, what about R times phi? Minus theta. You're very ready with it. Okay, good. So let's do it. So this goes away. And here I have minus h bar R times R versus theta is phi. And then I have 1 over R d in d theta. And the next one is R dot vector phi, which is minus theta. And then I have 1 over R sine theta. And then I have derivative with respect to phi. I write phi sometimes like this, sometimes like this. Okay? It's the same. Sorry for that. Okay, good. There we are. That's the end of the thing. So the angular momentum, okay, in terms of Cartesian coordinate, well, notice, here there is an R and here there is an R. Okay, so the R in fact goes away. Okay? So it's vectors theta and phi, which obviously contain only theta and phi, and no R, and derivative with respect to theta and with respect to phi. Okay? So R and dr are not there. Okay? Is it clear? So the angular momentum depends solely on theta, phi, and derivatives of that. Clear? Good. That was the goal of this rather long derivation. Okay. Now I could ask you, write Lx explicitly. Well, x component of this, for instance. What is the x component of phi? Well, this. The x component of theta. This. Okay, so I could write Lx. We want it explicitly. Here it is. Lx is equal to I h bar, the sine of phi, times the derivative with respect to theta, plus there is a cosine of phi, times look, there is the x component of theta has the cos theta, and then you divide by sine theta. That is called the cotangent of theta, derivative with respect to phi. Okay? That's it. This is the x component of the y angular momentum, and in the same way you can write Ly and Lz. Lz is particularly easy. Let's write Lz. Okay? So Lz is third component of this and third component of this. But phi has no third component. So the only thing that has a third component is this. So I have minus and minus is a plus. And the third component of theta is sine theta. It cancels with the sine theta. So let me write Lz because it's really simple. There it is. Okay? Lz is I h bar, the derivative with respect to the angle theta, okay, which describes the motion along the parallels, okay, the azimuthal angle. Pretty much, it looks like the momentum, right? But it's the momentum with respect to an angle coordinate, okay? This is particularly worth remembering, okay? This is obviously something that you find in the books or by Google, okay? And you don't want to remember it. But this, you might want to remember it, because it's particularly simple. Obviously, there is another object that will be useful in while, which is what is called the total angular momentum, the square angular momentum, which is Lx square plus Ly square plus Lz square. We'll see that this plays a very important role in a while. Being the square of objects that depend on theta and phi, this also depends only on theta and phi, derivative with respect to theta and derivative with respect to phi. Okay? You could write it, it's written in the notes, okay? But it's not particularly enlightening. Very good. But there is an important aspect now of the story, which is the following. Okay? So I erase most of it because we have understood the basic important things. The important aspect of the story is the following. L square as an operator and Lz commute. And in fact, L square commutes also with Lx and with Ly. So L square is an operator that commutes with any of the three operators that you want. Although, careful, the three of them then fight against each other. They do not commute. So you can pick up only one and pair it with L square. They nicely commute. And therefore, according to the theorem we said, you can form a common basis of eigenvectors of both. Let's verify that it commutes. This is equal to the sum of these three things squared. So Lx square plus Ly square plus Lz square, commutator Lz. Okay? How much is this? Well, it's the sum of the three separate commutators. Now, obviously, Lz square with Lz, how much is it? 0. Because an operator commutes with any power of itself. Good. So this you don't need. What about this? Well, that's equal to Lx square. So, let's put Lx out. Lx times Lx Lz plus Lx Lz Lz. I use the rule that I erased about commutator of product.
Lx.
And then the same thing with Ly, Lz plus Ly, Lz, Ly. Okay? Let's see, how much is this?
Minus
Minus I h bar Ly. And this is the same, right? Good. So, in fact, this thing is minus I h bar Ly Lx, and this is minus I h bar Lx Ly. These two terms. What about here? Here I have y and z, which is plus I h bar x. So Ly Lx because of this. And here plus yz, so same, I h bar Lx Ly. Good. They are exchanged, but luckily enough, this is here and this is here. Okay? You see? So the result is a very nice 0. And the same thing would hold for any of the components. But that's enough for us, because we tend to privilege Lz as a partner for L squared to commute. The reason is that it is certainly in the standard choice of the North Pole and theta and phi is the simplest object to look at. Okay? The derivative with respect to phi. Clear so far? Now, consequence of the general theorem about Hermitian commuting observables. Okay, these are Hermitian, by the way, I didn't tell, but angular momentum is an Hermitian operator. It's based on x and p, they are Hermitian. It is an Hermitian operator. Okay, so these are two commuting Hermitian operator like the A and the B before, right? I can find a common basis of eigenfunction of both. And this basis is written in the very same book of electrodynamics that I mentioned before. They are called spherical harmonics. Okay? So you can prove that L squared, a spherical harmonics of index L and M with angle theta and phi is equal to h bar square L plus 1, the spherical harmonics, theta and phi, and Lz, the spherical harmonic, theta and phi, is equal to h bar M, the spherical harmonic. Now, next time, I will show you that this is indeed the general structure of the eigenfunctions common to any two pairs of angular momentum, the square and the Lz. You might ask, what do you mean any two pair? There we have. No. You can have, for instance, the spin, which is not an orbital angular momentum, but obeys exactly the same commutation rules. And therefore, in principle, the eigenfunctions of spin admit exactly the same type of structure. You can have more than one particle, and therefore the angular momentum is the sum of the individual angular momenta of the particles. You can have a particle with spin, and therefore you have to sum orbital angular momentum and spin angular momentum. In other words, the world is rich of situations where you actually have an angular momentum operator which is not just the orbital angular momentum we have seen so far, but all of them, absolutely all of them, share the following property, that their commutation rules are given by this, okay? So whenever you see three operators, x, y, and z, whose commutator obeys this equation, like the orbital angular momentum, you call it an angular momentum. Whatever it is, it might be a very complex object made of several particles with spin, okay? Such an object is an angular momentum. We will develop the theory for an abstract angular momentum, and then we will specify it to the spin and play around a little bit, okay? So that's the strategy of the next lecture. Questions so far? No, the time is
Exactly.
okay. Good. So I'll see you next week. Okay.